for a square n by n matrix A, V is an eigenvector and lambda is an eigenvalue if, when you multiply A by V, the result is a scalar multiple of V. Anytime you see AV equals lambda V or AX equals lambda X, now and in the future, you're going to see this in future machine learning classes if you take them. Don't just memorize this as a random looking formula. Always remember that it has something to do with a linear transformation and preserving direction. Okay? The reason I say that is because what's about to follow seems more random and algebraic, but all we are doing is trying to find V's and lambdas for a matrix. Okay, if A is just some random matrix, how could I go about finding a lambda that makes this work? How could I try and find an eigenvalue and eigenvector pair? Starting with this. Yeah.
Could you like solve for V or like move lambda V to the other side?
Yeah, we're trying to solve for something, right? So like what can we do to massage this equation? Well, I can subtract lambda V from both sides. And indeed, I'm trying to solve for V in some sense. So also, what kind of zero is this? Zero scalar, zero vector, zero matrix? Vector, good, because this is a vector, this is a vector. Okay, can I factor out a V here? Yeah.
I feel like you would be able to.
Yeah, but the tricky thing is this doesn't seem like a valid operation. Why not? Yeah.
It's like a matrix minus a scalar.
Yeah, this is A is a square n by n matrix. Lambda is just a number like 7 or something. So this alone isn't valid, but how do we adjust it? Yeah.
Could you make it so it's like lambda times the identity?
Exactly, exactly. All we need to do to make this a valid expression is just add in this phantom identity. Okay, so now, let me write this a little clearer. I have A minus lambda I, times V is equal to 0. Okay, taking a step back. A minus lambda I times V equals 0. Big picture, if I squint, this looks like matrix times vector equals 0. What does that mean? Yeah.
V is in the null space of A minus lambda I.
Yeah, what this is saying is V is in A minus lambda I's null space. But what does that tell you about A minus lambda I? Yeah.
Columns are like linearly dependent.
Good. V is in A minus lambda I's null space. But what this means is that there's something non-trivial in A minus lambda I's null space, right? And I guess I should have started way back when I defined what an eigenvalue and eigenvector is. I should have started by saying we're not considering the 0 vector. Because any matrix times the 0 vector is just going to be 0 times the 0 vector, right? Because 0 times anything is 0. So, and I'll say, let's not let V here be the 0 vector. So back here, what this means is A minus lambda I has a non-trivial null space. And what I'm looking for are ways to figure out what the lambdas and V's are. And the tricky thing here is that we're simultaneously stating something about the lambdas and the V's. Maybe I can narrow down the problem and just first find a lambda and then worry about figuring out what the corresponding V is. So given that, if lambda is an eigenvalue and V is the corresponding eigenvector, and the fact that that implies that V is in the null space of A minus lambda I, and the fact that that implies A minus lambda I has a not useless null space, how can we try and find the lambda? Because it's true that yes, the deduction of all of this is that if lambda is an eigenvalue, then A minus lambda I has a non-trivial null space. But what can we do with that? Steve?
And A minus
Good.
lambda I is 0.
Right, I'm trying to figure out some algebraic way to figure out what lambda could be. And one of the many equivalent statements of a fact that a matrix is invertible is that its determinant is not 0. But here, we know that A minus lambda I is not invertible because it has a non-trivial null space, which means its columns aren't linearly independent. So what this means is that the determinant of A minus lambda I is 0. What this gives us is an equation that doesn't involve the v's, it doesn't involve the eigenvectors, it just involves the eigenvalues. Okay? And we can use this equation to solve for what the eigenvectors are supposed to be. Sorry, eigenvalues. Use this to find the lambdas. And this equation is so important that it's given a formal name. It's called the characteristic polynomial of the matrix. Okay? Let me make sense of that. So the characteristic polynomial of A is the polynomial whose inputs are lambdas and outputs are, numbers, is the determinant of A minus lambda I. And what we are looking for are the zeros of the characteristic polynomial correspond to eigenvalues, lambda. Right? We're looking for the roots of the characteristic polynomial. That is, we're looking for where the determinant of A minus lambda I is 0. Okay, that's an abstract idea. Let's just make up a matrix and apply this idea to it. We'll stick with A equals 1, 2, 2, 1. The determinant of A minus lambda I is the determinant of this matrix. 1 minus lambda, 1 minus lambda, 2, 2. Do we agree that subtracting by lambda I is equivalent to subtracting by lambda on the diagonal but leaving everything else the same? We convinced of that? Okay. What does this end up being? It's 1 minus lambda squared minus 4. We agree with that? Okay. Expand this out, you get lambda squared minus 2 lambda plus 1 minus 4, which gives you lambda squared minus 2 lambda minus 3. Where is that equal to 0? Well, you could use the quadratic formula, but usually in by-hand examples, we'll try and make them factorable. And this to me looks like plus 1 minus 3. So when I set this to 0, I can just read off the lambdas. Lambda equals minus 1, lambda equals 3. Okay? And this characteristic polynomial gives us insight into how many eigenvalues a matrix could have. There's a fact from, some high school algebra class, which says that a degree n polynomial can have up to n roots. That is, it can cross the x-axis at most n times, right? A line can cross the x-axis once, a quadratic can pass it twice, a cubic can pass it 3 times, so on and so forth. And in the cases where it doesn't pass it n times, well then either it has some complex roots or it has a double or triple root. Okay? And so all of those are possibilities with the characteristic polynomial as well, but let me emphasize that this is a degree n polynomial. Okay, so I have an idea. Why don't we look at the matrix 4, 1, 0, 4 on the diagonal, but zeros everywhere else? What do you think its characteristic polynomial is? Technically, yeah, we need to, take the determinant of a 4 by 4 matrix But if we think about what the determinant represents and how it represents a volume scaling factor, since we have zeros off the diagonal, we can think of each component independently. And so the determinant of a minus lambda I is just going to be what? The determinant of a diagonal matrix. It's going to be the determinant of this. 4 minus lambda, 1 minus lambda, 0 minus lambda, 4 minus lambda. What is that going to be? Yeah.
Is it the sum of the diagonal?
Not quite. It's related to the diagonal, but it's not its sum. Right? Imagine if I had the matrix 1, 1, 0, 0. Its determinant is not 2.
Oh, it's the
Product. Yeah. For a diagonal matrix, the determinant is the product of the diagonal. Because you can think of, remember, the determinant describes the total amount that the volume of the unit square or cube or box is stretched. Here we're stretching it, the first coordinate by 4 minus lambda, the second coordinate by 1 minus lambda, the third by 0 minus lambda, and so on. Right? It's more complicated if it's not a diagonal matrix. But here, it is diagonal, and so we can write this as 4 minus lambda, 1 minus lambda, 0 minus lambda, 4 minus lambda, which simplifies. I can write this as lambda, lambda minus 1, lambda minus 4 squared. And in fact, yeah, that's fine to write. I've pulled out a negative 1 out of each of these, but there's 4 of them, which means they all cancel out. Are we in agreement here that this is the characteristic polynomial of this matrix? Okay, but what does this look like? Because it has roots of 0, 1, and 4, but something is different about the root at 4. Right? What does it look like? Well, we'll try and draw it. This is our lambda axis here. This is our p of lambda axis. And remember, we're drawing p of lambda equals lambda, lambda minus 1, lambda minus 4 squared. Okay, I need to somehow draw. Maybe I'll draw the y-axis somewhere a little to the left. I need to draw a polynomial with roots at 0, 1, and 4. Okay? And this is a degree 4 polynomial, which means the tails in both directions point in the same way. So they're both going to move up. So out here, this is going to extend infinitely. And out here, this is going to extend infinitely. How do you think I fill this in? Yeah.
The parabola touches 4 and goes back up instantly.
Yeah. Well, let me start from the left because it describes what a regular root looks like. Like a regular root would look like this. We go underneath. We come back up. But here's what's going to happen. It's going to come touch the root at 4, but not cross. And so, at 4, we have what's called a double root. Is this a familiar idea from high school algebra? Okay. So here, this tells us lambda equals 0 is an eigenvalue. This tells us lambda 1 is an eigenvalue. And this tells us lambda is equal to 4 is a double eigenvalue, if you will. The more formal term is that 4 is an eigenvalue with algebraic multiplicity. I didn't make this up, I'm just telling you what it is. 2. So the algebraic multiplicity of an eigenvalue is the number of times it's a root to the characteristic polynomial. So if this said lambda minus 4 cubed, well then 4 would be an eigenvalue with algebraic multiplicity 3. Do we agree with that? Okay, we're going to focus more on this on Tuesday, but again, it's something that's going to you're going to start to see it on homework 10, so if you start it on the weekend, you'll need to know what that is. Notice, I'm not just calling this the multiplicity. I'm calling it the algebraic multiplicity. There's a different type of multiplicity as well, in addition to algebraic, and it's called the geometric multiplicity. Okay? And the geometric multiplicity actually goes back to your earlier point, which is that it's possible for there to be multiple directions of eigenvectors for a possible eigenvalue. And the geometric multiplicity is equal to the number of independent directions for one eigenvalue. Okay, and it turns out that the geometric multiplicity is always less than or equal to the algebraic, meaning lambda equals 1 here can't correspond to two different eigenvector directions. Neither can lambda equals 0. But lambda equals 4 could. It could correspond to, it could have two eigenvector directions that are not the same direction. And the space of eigenvectors for lambda equals 4 could be a plane or a two-dimensional subspace. But it's not guaranteed that it is. Okay, it could be, it could not be. And there's a special type of matrix where it is as big as it could be, and that's called a diagonalizable matrix. And we'll see that again next week. I'm just sort of giving you a roadmap of where we're going. Anyways, this is a 4x4 matrix, A, from back here, but it only has 3 distinct eigenvalues. One of them just has an algebraic multiplicity of 2. Can you think of a matrix that has no real valued eigenvalues or eigenvectors? Yeah, there's plenty of examples. I mentioned that a rotation matrix is a good example. How about this? 3, -4, 4, 3. This is not an orthogonal matrix, but it's just a scalar multiple of 1. This is 5 times 3/5, 4/5, my favorite default example of an orthogonal matrix. Right? These columns are both unit vectors, and they're both orthogonal, which means this is an orthogonal matrix. So this is a rotation and then a stretch. And it's a rotation by something that's somewhere between 0 and 180 degrees, which means there's not going to be an eigenvector in the real number sense. And if you compute the characteristic polynomial, what do you end up getting? You get 3 minus lambda squared plus 16. You agree with that? Okay. But could that be 0? Well, if you expand this out into lambda squared minus 6 lambda plus 9 plus 16, I don't know, maybe you'd sit around trying to factor this, right? Though, of course, it can't be factored. But if you just look at this form, what this tells you is box squared plus 16. But box squared can't be negative. It has to be 0 or greater, which means this is 16 or greater. Right? This is a polynomial. Again, this is in the lambda p lambda space, whose vertex is 3, 16. Which means it doesn't have any real valued eigenvalues. Okay? And if a matrix doesn't have any real eigenvalues, those eigenvectors also aren't real. So there are 2 complex eigenvalues and 2 complex eigenvectors. But in general, if an eigenvalue is complex, the vector will be complex too. And if it's real, they'll both be real or they'll both be complex. Because the matrix is made up of all real numbers. So if the eigenvalue it has complex numbers in it, the eigenvector has to have complex numbers to cancel out the original complex numbers. Otherwise, we'd have complex numbers here, which in our class we won't. Okay? Now, if you're familiar with complex numbers from some other class, then the complex valued eigenvalues in this matrix are of the form 5e to the I theta and 5e to the minus I theta, where theta is whatever angle corresponds to this rotation. I think cosine inverse of 3/5. Not a relevant fact for us, but if you happen to know what that is, just could be interesting. Okay, but we're not going to talk much about complex numbers. Other than that, eigenvalues could be complex. Okay, so the big point here is that the characteristic polynomial tells us the nature of the eigenvalues of a matrix. It tells us what their multiplicities are. That is, if an eigenvalue is repeated, this is the situation in which this is a possible situation you could end up in. And it also tells you if there are no real valued eigenvalues. Though in general, every n by n matrix has exactly n eigenvalues. It's just that some may be duplicated and some may be complex.